Now we have seen how to solve a system of linear equations if the matrix has complex eigenvalues. So if you are supposed just to solve a system, then that's the best way to figure out the complex solution and then take its real part and its imaginary part. Well, but suppose that we only have a system of two equations, so it is on the plane, and the complex eigenvalues are complex, so which means that we have our recipe. So in order to solve it, what we need to do, we need to find one of the eigenvectors, suppose it is xi, right? And then we take xi times e to the rt. So here r is an imaginary number, a complex number, and then we take its real part and its imaginary part. So that's the full recipe for the solution. But it's not very easy to sort of to link to a picture, right? So if you just try to imagine how it's going to look like in terms of the face portrait, you can't say, right? So what is the real part and imaginary part? So that's why we're going to come up with a little bit more a specific formula, right? And if we just apply all these findings, if we just link them together, right? So then, this is going to be the real part, and this is going to be the imaginary part. So what it means that we have two real linearly independent solutions. And now it's a bit more clear to, it's easier to understand what's going on because, in any case, we have this multiplier in front, e to the rt, and of course, if r is positive, so there could be three cases. If r is positive, then we're just going away from the origin. But since we have cosine and sine inside, and of course, as t goes by, so cosine and sine, they go around the origin. So we have a combination of motion that goes from the origin and around the origin. So then it's going to be something like a spiral. So, but if r is negative, then e to the rt, as t goes to infinity, approaches 0, and then because of the same logic, there is going to be a spiral that goes towards the origin. And of course, if r is 0, then this term just disappears, and we have a periodic motion around the origin. So let's verify this observation and see the actual plots. So here is my first example. And again, this is a straightforward calculation, so I'll go through it very quickly. Right, so here is my eigenvalue. So, sorry, the eigenvalue is the real part of the eigenvalue, and here is the imaginary part of the eigenvalue. So the two eigenvectors are here. So we just take the two, not the two eigenvectors, the real and the imaginary part of the first eigenvector. So let me emphasize that. So that's the first eigenvector. Its real part is A. So that's the real part. And the imaginary part is B. So that's the imaginary part. And now we just substitute all these numbers into the formula that we produced in the previous slide, and then here is what we got. So here is the general solution, and of course, by varying the values of C1 and C2, you can try to find a few particular trajectories, but basically here is how it looks like. So we do have spirals that go away from the origin. All right. So here is my next example. So again, now if we compute the two eigenvalues, and well, here is just one eigenvalue. So of course, R2 is going to be the same thing, but with minus I. So minus 0.5 minus 0.5 I. Right. So then we can write down the real and the imaginary part of the eigenvalue and the real and the imaginary part of the eigenvector. And then we just substitute it to the formula, and then we get our two linearly independent solutions, which is the basis in the space of solutions. And then by just multiplying one of them by C1 and then the other one by C2, we get the general solution. And then, so now varying C1 and C2, where we can construct a few particular trajectories just to plot. And here is how it looks like. This is the phase portrait. These two directions, they kind of have to do with eigen vectors of the matrix AB. So A is 2, 1, B is 0, 2. So if we write down it as a matrix, 2, 1, 0, 0, 1, right? So this is A, which is the real part of the eigenvector, and this is B, which is the imaginary part of the eigenvector. So then, if we plot eigenvectors of this, no, it's not eigenvectors, or we just plot them. Okay, yeah, I think we just plotted them. So this is A, and this vector is parallel to B. So as you see, they are not perpendicular anymore, so which makes the whole thing a bit skewed, so to say. So this is as compared to the previous example. So notice that here A and B are perpendicular. So then the spirals, they're kind of more round, and here the spirals are a bit skewed. All right, here is one more example. So now notice that if you compute, if you look at the trace of the matrix, then the trace is 0. So which means the characteristic equation is R squared plus something is 0. So the two eigenvalues are going to be purely imaginary. There's not going to be a real part. But the eigenvectors, they may not be perpendicular, or so the eigenvectors are non-trivial. So anyway, so the fact that the trace of the matrix is 0, it means that the eigenvalues are purely imaginary, and then it means that this multiplier e to something t is just missing there. So it's not going to be there, and the trajectory contains just sine and cosine, a combination of sine and cosine. And of course, these are periodic functions, so as t goes to infinity, they're just moving around the origin. And here is what we see. All right, so now let us summarize what we've seen. If the coefficient, if sorry, the real part of the complex eigenvalues is positive, and the real part of the complex eigenvalues is actually just 1/2 of the trace of the matrix. Then trajectories are spirals going away from the origin. If it is negative, then spirals going towards the origin. If 0, then trajectories are ellipses. So the magnitude of R, so how big it is, let's remember that it is e to the power RT, so it has to do with how fast they they go away or towards the origin. And well, mu it has to do with how fast trajectories rotate around the origin, but that cannot be seen on the phase portrait. And the vectors A and B themselves, they kind of have to do with skewness. So if it is round or it is a bit distorted. So a little challenge for you to think at home. We are not going to cover it in further lectures, so we're not going to apply it in the project or anything. It's just for you to think about. So the first challenge, and here is the second challenge. So recall that the last week I've taught you how to sketch the phase portrait if the eigenvalues are real. So now, as we just saw, we can figure out the type of a phase portrait by just looking at the real at the complex eigenvalues too, but we cannot really sketch it. So